Today's tutorial is about MOPs Apply Attributes DOP. In MOPs Plus, much of the functionality of MOPs has been ported over to the DOPs context for use in simulations. The end goal is to provide you with easy ways to manipulate points impact primitives in simulations using MOPs-like controls to generate physical forces that can react to things like collisions, gravity, vector fields, and so on. It's important to remember that the DOPs timeline doesn't work the same way as the SOPs timeline. When you create any kind of solver in Houdini, you're setting the initial conditions of the simulation in SOPs, and then as soon as you jump over to DOPs, you're working in a different timeline. The nodes you set up in DOPs are going to execute on a per time step basis. This is very different from SOPs, where the entire graph is evaluated at each frame, independent of any other frame. The most obvious difference is in how falloff values work in DOPs. If you apply a MOPs goal position to an object with a falloff of 0.5, that means that the object is going to translate 50% of the distance to the goal per time step. It's very important to remember this difference. Most of the MOPsDOP system is powered by one central node, the MOPs Apply Attributes DOP. This serves a very similar function to the MOPs Apply Attributes SOP from the open source MOPs package. You define goal attributes in a falloff, and apply attributes will blend transforms to reach those goals. With the Apply Attributes DOP, you're still defining goal transforms in a falloff, but you also get to choose how you want the solver to reach those goals. You can directly blend transforms like you do in SOPs, or you can generate wind forces, or you can use old-fashioned force and torque to drive the simulation. You can also use certain triggers to force points to stop colliding and snap into position for simulations that need to end in very specific lockups. It takes a little while to understand how this node works, but once you get it, most of MOPsDOPs will make a lot more sense. Okay. Before I get started, I want to point out that the examples that I'm going to be building are going to be based on the existing examples in MOPs Plus, which are MOPsDOPs examples and MOPsDOPs examples 2.hip. So if you ever need to see a little bit more detail in the setup, open up those files, and those are going to be pretty much equivalent to what I'm building in front of you now. So for the first example, I'm going to show you how to make objects meet goals using apply attributes, something really simple. So we're going to start by dropping down a geometry container, and then a box. Let's add vertex normals so that we can see them when we instance. I'm going to create a Mops Instancer, and then set the distribution to be, let's make this a 10 by 10 instead of a 1 by 1, and then set the sep size to 2 in X and Z, and this is going to make us a nice grid of boxes here. The next thing I want to do is create our initial, well, these are our initial conditions for the simulation. What I want to do now is create our goal. I'm going to do that using Mops randomize. So really quickly, let's just randomize the position. Let's do this from -5 in Y to +5 in Y, and then randomize orientation, and let's also randomize scale. And I just want to set my minimum to be a little bit larger than that. I don't like things going down to 0 when we're dealing with physics. So yeah, that looks fine. So these are going to be our goal conditions for the sim. So now I'm going to drop down a DOP network, and this is where we'll do our simulation. We'll plug the instancer in the first input and then randomize in the second input. So something really important to point out for MOPsDOPs in general is that if we look at our instancer here and then middle mouse to see our attributes list, we have all these attributes that we'd expect that are sort of mirroring the packed transforms. We have scale, p-scale, orient. As of Houdini 19, if you're trying to do a bullet sim, which in this case is what we're doing, and you have these attributes on the points, these will affect the simulation. So it's really important if you're trying to get a predictable result from bullet in Houdini 19 or later, that you delete those attributes. So I'm going to drop down an attribute delete and just wipe out any template point attributes. So that's going to be orient, p-scale, and scale. I don't think up or n really matter for this. I could delete up just to be safe, but these are the big ones that are going to affect the simulation. So I'm just going to wipe all of those out and then go to my DOP network. So first, I need an Rbd packed object. I'm just going to grab this guy here. And then what I'm going to do is set the geometry source from just generic SOP to first context geometry. That means that it's going to get the array of cubes that I set up going into the first input. The next thing I'm going to do is drop down a rigid body solver, and then wire it into the first input here, and then just wire this directly to the output. And there's really not much I need to change about the solver. So now I've got all my starting objects here, and if I run it, nothing happens because we don't have any forces at all. So what I'm going to start with is MOPs Apply Attributes. And this is going to be our main force here. I'm going to wire it to the pre-solve input. And let's just take a look at the interface really quick here before we go any further. At the top here, we have some things that you might expect from most pop operators. You have an activation parameter, which is really important. This is the same as the activation parameter for any other DOP in Houdini. So if it's anything other than 0, this solver is going to take an effect that time step. You can use this basically as a keyframeable bypass flag. So if you want to turn off a node for any length of frames or any length of time during the simulation, just set activation to 0 and keyframe it, and then you can keyframe it to any other value when you're done. You can use expressions here, that's totally fine. It's just, if it's anything other than 0, it's going to take an effect that time step. The only special thing here that you might want to pay attention to is the match by. This is similar to match by in the rest of MOPs when you're in SOPs land, in that this is the attribute that it's going to use to line up the goal with whatever is in your simulation. By default, that's set to name, because most of the time with MOPsDOPs, you're probably going to be dealing with RBDs, but not always. And the reason for this is that the ID, especially in versions of Houdini prior to 19, the ID can sometimes be reset. Most notably, if you try to adjust the scale during a simulation, MOPs is going to reset the ID attribute as a sort of a hack to force the collision geometry to regenerate. Because of that reason, when you're dealing with RBDs, you generally want to have this be matching by name. But you have the option to match by whatever you want, and if you're dealing with something like a Vellum simulation, you may want to set this to ID instead, because generally speaking, regular particles don't have a name attribute applied. Anyways, let's keep going. Under transformation, these are basically your basic toggles and modes as far as what do you want to affect. So do you want to affect translate, rotate, scale, pivot? And how do you want to affect them using the attributes defined by apply attributes here. And that means that you can either add or set translate, you can add or set rotation. Most of the time you don't need to deal with this. This is more API level stuff because a lot of the rest of MOPsDOPs relies on being able to accumulate or directly set transforms. But if you were trying to build up your own effect, you could use these to create some pretty interesting stuff. But for the most part, you could ignore these if you're not trying to build your own nodes. Let's go over to force update real quick. This is where a lot of the interesting stuff comes in. This is basically telling MOPs how do you want to compute the forces that are going to affect the simulation. By default, the update mode is set to velocity spin, and that means that it's going to more or less compute the velocity and angular velocity that each one of these objects needs to be at in order to meet the goal. And once it computes those forces, it's going to scale them by falloff and then apply them to each of your objects. By default, treat as wind is also enabled, and that means that rather than just directly setting the V and W, or the velocity and angular velocity attributes, it's going to affect target V and target W and the air resist and spin resist attributes. What that more or less means is that it's going to try to blend in. It's going to set a goal velocity and then blend your existing velocity in with that goal, depending on how high your resistances are set. And this works exactly the same way as any other wind force in DOPs when you're dealing with pop wind or any other related force in DOPs. They're using exactly the same settings, same math, same attributes. The next tab over is the Falloff tab, and this is really simple. It's just saying what attribute do you want to use as the Falloff attribute, and do you want to use it at all? And Falloff is going to take whatever force we choose to generate, whatever goal force, and basically scale it. So it roughly works similar to how it works in SOPs, but it's not exact, and it is applying this per time step. So I know I mentioned that in the introduction, but it's really important to remember that. It means that your falloff values when you're working in DOPs are typically going to be lower than what you're used to. You're not generally going to want to have a falloff value of 1 unless you really want something to snap into place. And the last tab is the inputs tab, and this one is really important. This is basically saying what is my goal coming from. So my target geometry is my second context geometry by default, and that means whatever I wired into the second input here. So this is my goal. And the geometry is basically what DOP data do I want to affect with this solver. You could, in theory, use this to affect constraint geometry as an example, and that's the name of the DOP data that's involved in building constraints for both Vellum and RBD. 90% of the time, what you want to affect is geometry. This is exposed so you can change it, but you almost never need to bother with this. Most of the time, you're going to be changing the target geometry, And this can be one of the context geometries from SOPs, whatever's wired into the DOP.NET, or you can directly point to a SOP path or even a DOP data path if you want to. I'm going to turn this back to second context geometry. So if I run this as is, you're going to see that they're very quickly and rigidly going to sort of pop into the positions that we set randomly. I'm just going to jump back here and then template this so we can see it a little more clearly. So they're going to try to get to those positions, and they're going to oscillate a bit. And the reason they're oscillating is because on each time step, they're sort of trying to get exactly to that position as quickly as they can. So they're trying to get to that, but they're going to overshoot just because they have a little bit of momentum. That wind force mixing isn't 100%, and so they're going to bounce around a little bit. If I go into the DOP.NET here and go to force update and crank my air and spin resistances, that's going to sort of slow them down a little bit, but it's also going to make them oscillate less. So they're going to try and meet those goals, but they're going to oscillate a lot less because the new target force is being blended in so much more quickly. They are going to still bounce a little bit, and another thing that we can do to maybe slow that down is add in some pop drag. And again, this means that it's going to potentially slow down how quickly these things can initially meet their goals. But yeah, it's going to slow down the oscillation just a hair. This air resistance is pretty low, so we could crank this, and that might affect it a little bit differently. Yeah, so they're going to be a little bit mushier going into that position, but then they're going to oscillate significantly less. And this is like working with wind forces anywhere else in DOPs. It's hard to be perfect about it. I'm just going to disable this drag temporarily and then go back to apply attributes. So the other update modes, the reason why this is the default, you have options here to set them to other things, but the reason why this is default is because force and torque, if you're used to working with pop forces, are pretty hard to direct. And as an example, let me just hit this with the same values as before, and you can see it's oscillating like crazy. And that's because what it's trying to do is apply a force, which gets added to velocity at each time step. And so it's going to oscillate like crazy. It's going to overshoot because the force gets to be so strong halfway through this. And then it's going to try and get back to where it overshot and then shoot back in the opposite direction. And it has so much force being applied to it that it's going out of control. If you do need to use force and torque, you almost always want to have drag. So we could do just regular drag forces. We can do pop drag and pop drag spin. And these are going to help contain those forces a bit. I'll have the resistances all set to about 10, which is pretty thick. And that way they're going to reach that, but they're going to fight it a lot less. Okay, let's just turn these back down to 1 and then set our force update to something else. For position and rotation, it's not going to compute forces at all. It's literally just going to shove your objects exactly to where they need to be. So you can see that it's instantaneous. They immediately hit the goal and they don't oscillate at all. The advantage of this is that obviously you have very precise controls over this. So you can tell these things exactly where you need them to go. The downside is because they're not really moving to those positions, unless you control them at the goal level in SOPs, you might miss collisions, or you might accidentally knock things around and have them jitter a lot. If they're unable to reach their goal for any reason, they're going to fight it pretty hard and you'll see jittering in the viewport. So if I don't want this to meet that goal that fast, what I can do is drop down falloff nodes. So MOPsDOPs has falloffs exactly the same as regular MOPs. So for example, I could do a plain falloff here and wire this in at the beginning, and this is just going to make it so that I don't meet those target goals quite as quick. So for example, if I set this to 0.5, that means that it's going to compute the force to meet halfway between that goal on each time step. So here's 1, and now here's halfway between this and the goal, and then again and again. So it's not going to get there in 2 frames. It's basically going to sort of approach it over time until it gets so quickly that, or until it gets so close that you can't even notice the difference. Falloffs are a little bit less exact. It's harder to basically say get there in exactly this many frames, because it's basically saying get halfway there, now get halfway from that, now get halfway from that. And so it's more of like a roll off over time. So for this second example, we're going to take a quick detour and use one of the MOPsDOPs forces that relies on apply attributes inside its UI. And you'll see what I mean in a bit, but this is going to be one of the forces that's a little bit higher level, but the controls of the inside are going to look a lot like what we were dealing with the apply attributes DOP. what we're going to do is just generate a simple noise force and use that to push these objects around using Falloff to control how much noise is applied. So first we've got to set everything up in SOPs. I'm going to drop down a geometry container. And then inside, we're going to just make sort of an array of test geometry. So I'm going to do a pig head and a rubber toy. I'm going to set the pig head to be easy so that we don't have to deal with the eyes. And then on the rubber toy, we can stick with hard, but I'm just going to turn off the shader. And then the pig head doesn't have normals, but the rubber toy does. So I'm going to drop down a normal SOP and just correct that. And then we'll wire both of these guys into an instancer. And let's just make this instancer a lot bigger. Let's go to the distribution tab, and then under size, we're going to make this a 20 by 20 grid. And then I'm going to bump up the step to be about 1.5 by 1.5. And then those pig heads are a little bit too big, so I can just go to the instancer here, the options for the pig head, and maybe take that scale down a bit. And the other thing I'm going to do is, because these guys are oriented a little, they're sort of positioned a little bit differently around the origin, what I'm going to do is just enable center instance for both of these. There, that's a little cleaner. The next thing I'm going to do is just drop down a MOPs randomize, just to make things a little bit more interesting. We're just going to randomize uniform scale. I'm going to set the minimum value to be, maybe 0.5. Just to break up the pattern a little bit. The next thing I'm going to do, because I'm running a physical simulation on this, and these things, especially the rubber toy here, are fairly complicated. They're not going to collide very well, especially like all these little fins and points and things like that, because they have a lot of concave sections. So in order to quickly clean that up, I can use a MOPs node in MOPs Plus called MOPs Collision Geo. I'm just going to drop this down here, and then if I preview this, you can see that this is sort of what the collision geometry is going to look like by default. What I'm going to do is drop the triangle size to be about half what this is. So you can see that I'm getting a little bit of detail coming back. And then I'm going to just keep dragging the max concavity down to, let's say, about 0.1. And now you can see that these are sort of the compound shapes that have been generated from this. If I turn on preview segments, you can see that what it's doing is generating a bunch of convex hulls and then just kind of gluing them together to make one big primitive shape. But this is exactly what Bullet wants to see. It has a lot of an easier time thinking about things as groups of convex hulls than it does trying to compute concave shapes. It has a really hard time with those. So now that I have this collision geo defined, what I'm going to do is basically set this up just to go right into the DOP net. So I'm going to create a DOP network and plug this in. And if you remember from before, these things have, or could have, it looks like these guys don't have attributes that I'm worried about right here. So we don't have to worry about deleting it just yet. I don't see any template attributes, so we can leave that alone. So let's just go inside. I'm going to make roughly the same setup as before. I have an Rbd packed object, and that's going to be coming from the first context geometry. And then I have a rigid body solver. I'm going to wire that into objects, wire this into the output. There's all of my objects ready to go. Now, one thing I'm going to do on the solver to make sure that all of these groups of objects solve together the way I want them to is under bullet data, I'm going to enable create convex hull per set of connected primitives. This is going to make sure that each one of these big globs of pieces here solves as a single piece. Okay, now I'm going to drop down a MOPs Plus noise modifier. And this works a lot like the noise modifier in SOPs, but this is going to be applied to each of these objects per time step. So I'm going to wire this in to the post-solve input. You could do pre-solve if you wanted to. There's subtle differences between the two. If you want, you can be consistent, wire this to pre-solve, whatever. It doesn't make a huge difference for this particular simulation. Now, under the noise tab here, this is going to look more or less like the MOPs noise modifier does in SOPs. You have the ability to choose what things you're affecting, position, rotation, or both. You can use a rest attribute to look up the noise, or you can look up the noise field in world space. You can pick from a whole bunch of built-in noises that we've made for you. And then you can optionally make this time varying. So if you wanted the noise to cycle, you could do it that way. This is all basically the same as what's coming from SOPs. If you go to the forces tab here, this is going to look familiar to you because these are the same exact parameters that you have on the forces tab for apply attributes. A lot of the extra attributes have been sort of stripped away because the noise field isn't relevant there. But you still have a fall-off attribute you can pick. You have your update mode, which is really important. You have your resistances, because this is a wind force, and you have overall scales that you can apply to each force. Your translate force scale, rotate force scale. You also have the option to turn on Vexpressions here. Most MOPs-DOPs have this built in, and this allows you to sort of fine-tune any of these values per primitive. And this hint here tells you what attribute is bound to what. So if you want to adjust the fall off for each thing or the air resistance for each thing, you could just uncomment this line and replace this with whatever Vex expression you'd want to use. I'm going to turn this off for now. So I'm going to go back to the noise tab, and then let's crank the amplitude to make this a pretty strong noise. I'm going to turn the aim weight up to 0.5, and aim weight is basically saying how much do you want this noise field, like the directionality of it, to affect the orientation of each object as it moves. So with 0.5 is pretty strong. This means that these things are going to try pretty hard to match the orientation of the noise field as it moves through it. And then I'm just going to drop the frequency down to about 0.3, which I know in advance is just good for this scene scale. I'm going to zoom out a bit here, and let's run the sim. So you can see that these guys are just going to sort of be wildly careening through this noise field, and they'll collide with each other along the way. Now, one thing that we can do here that I wanted to touch on is we can use Falloffs to determine how much of this noise gets mixed in. Because again, any of these MOPs forces, when you compute the force that you want to use to reach the goal position, you can apply a Falloff to it, and that'll scale the amount of force that's applied. So for example, if I use a plain Falloff here, I could set this to be, let's say 0.1. And now when I run the simulation, these guys are going to move a lot more slowly. These values, of course, can be keyframed, so I could start with a really low value and then crank the amount of noise over time. For example, let's bring this up to 0.5 a little bit later in the sim and then rerun it. And you'll see that the force mixing starts blending in a lot harder over time. Another thing that I kind of touched on earlier but didn't really elaborate too much on was on the noise modifier, for example. I could have this noise running until, let's say frame 72, and then just use the activation parameter here, set a keyframe on it, and then after frame 72, just set this to 0, or use an expression, whatever you like to do. And now the noise field is going to start slow, ramp up, and then suddenly stop, and everything is just going to continue along where it already was. You can see that although they're still moving, they're not changing direction anymore. They're just flying straight out. And of course, plain Falloff is pretty boring. We can do better than that. So let's try turning this off. And then, for example, we could use a shape Falloff. And this works just the way that you'd expect it from stops. So I'm going to turn on preview Falloff. And then you'll notice that if you have the Falloffs on here, you don't actually see anything update just yet. And that's because when you're working in DOPs, unless you specifically tell the object that you want to solve on the first frame, nothing has actually happened yet. So I would have to actually go to the rigid body solver, possibly the rigid body object, yeah, here, and then solve on creation frame. And now you're going to actually see these things. If I rewind here, oh, you know what, I have to tell the collision geo not to preview segments, and then dive back inside. Now we're going to be able to see the Falloff values in here. And so let's increase the shape here. Let's make the scale much bigger. There we go. So now we're getting a broad range here, and the Falloff works the same way. Over here it's 0, where it's using this purple. Over here it's close to 1, where it's red. And this is just showing how much of the Falloff is going to get applied. I'll just move this to full 10 so that we're getting a full spread here. And now with this in place, if I run this, you can see that these guys move a lot, and these guys are barely affected by the field. So this is sort of same MOPs principle you're already used to from SOPs. The higher the Falloff value, the more of that force is going to get mixed in. I'm going to disable this really quick. There's also, of course, a noise Falloff that we can use, which is a really good way of creating sort of organic-looking effects. I'm going to set the noise frequency to be pretty low. And then I'm going to enable time varying so that the noise is cycling over time. Let me just set this back to the beginning. I'll leave the time varying scale alone. And then I'm just going to turn on preview Falloff so we can actually see the field evaluate over time. And it's a little bit low contrast, so I can go in here to remap, turn this on, and then maybe I'll just drag the edges in here a little bit so that we get a bit more contrast in the movement. There we go. Now if I play this, you can see that as the field evaluates, these things get pushed around more or less. And it might be even easier to see that if I add some drag after the fact. So I can add a drag and a drag spin. And now when the noise field isn't affecting them directly, they're going to sort of take a pause much sooner than they did before. Of course, activation is still keyframed, so I'll want to delete that, set the activation to 1. And there, now we're going to see these things moving a lot more. Anytime they turn red, they're going to get this little burst of energy. So let's say that this is the simulation that we want. We go back to the geometry level here. We have our DOP net, and everything is basically looking good, but you'll notice that these aren't our real objects. These are still these sort of proxy objects that we've built. So now we have to take these attributes that we've generated from this simulation, these transform attributes, and apply them back to our original geometry up here, or actually after the randomize is when we would start. So the way that we can do this is just using vanilla MOPs nodes. I'm going to use extract attributes, and this is going to take the template point attribute. It's going to take the packed transforms from the simulation and turn them back into template point attributes that MOPs can read. And then I'm going to make an apply attributes here, and I'm going to take the original high resolution geometry, so before the collision geometry, this is our original stuff. And I'm going to wire extract the result of the extraction to the second input. So these are the template point attributes that MOPs wants to see. I'm going to change match by ID to match by name. Because I'm working with RBDs and the ID attribute, in this case, isn't being reset, but with RBDs, it's a good idea to just match by name. And then I'm going to go over to the attributes tab, and I'm just going to copy the color attribute across so that we can see the same colors that we saw before in the sim. And now if you look carefully, you can see that this is the high-res geometry being manipulated by that same simulation. So a real easy way when you have MOPs collision geometry to generate proxies, you run those through your simulations, extract, and then apply to your original geometry. And now you have your high-res simulation geo moving, or your high-res geometry moving around to match the simulated geo. For our next example, we're going to create this effect. So we have this grid of pig heads, and we're going to scale them up using a sort of noise force. And then when they're not scaling, they're going to be gold back into their original position. So you get this sort of oscillating grid of pig heads scaling up, colliding with each other, and then moving back to their original position and orientation. So first things first, let's drop down the pig head and an instancer. Wire these up. On the instancer, we're just going to turn the global transform down to maybe 0.07. And then we'll make this a 2x2 grid so we get a few more pig heads, enough where we can actually visualize the noise field a bit. Next up, we're going to make a MOPs collision geo so that we can make our collision proxies. And then the triangle size for this can probably be about 0.3. That's probably enough detail. And then just drop the max concavity until we get something that roughly looks like the pig head. This should be plenty of resolution for what we need. Next up is the DOP network. So real quick, I'm just going to middle mouse on this to see what attributes I have. It doesn't look like I have any template attributes on these collision proxies, so I'm not going to worry about deleting the attributes before I go into the DOP net. You can do it every time just to be safe. It doesn't hurt, but in this case, I don't actually need to do it. What I am going to do for the goal, though, is because I don't have those attributes here, like the orientation, I'm going to drop down to MOPs extract attributes and wire this in to the second input, because the second input, this initial state here, is going to be my goal state for one of the operations I'm doing inside. So I'm going to make sure to extract this and then wire this in as the second input. And then for the first input, it's just going to be this stuff as is, because I don't have any template attributes that are going to get in the way. So let's go inside the DOP net. First things first, Rbd packed object. I'm going to set the geometry source to first context geometry, which is going to get that initial group of pig heads, and then a rigid body solver. We'll wire this up, and now I have my initial conditions for the sim. So the first thing that I want to do is I want to set up that force that's going to scale these things up over time. And I'm going to do that using a noise falloff to create the actual noise pattern first. So let's wire this in. I'm going to enable falloff preview. And then the other thing I need to do if I want to actually see this is make sure that this solves in the creation frame. And now I can actually get a preview on the first frame here of the falloff in place. On the noise, I'm going to leave it at perlin and pretty much just leave all this stuff as is, but I'm going to enable time varying, and let's just set this to be 2, so it's going to evaluate reasonably quickly. The other thing I'm going to do, just so that I'm getting like a full range of noise here, is on the remap settings, I'm going to enable this and set this to be about 0.1 minimum to 0.7 max, and this means that I'm going to get a more contrasted spread of noise here. And what I'm going to do is use this noise field to drive a MOPs transform DOP. This works just like the transform modifier in SOPs. Exact same kinds of controls, but you have this forces tab that resembles exactly that same stuff we went over before with apply attributes. What I'm going to do is transform these things by about 1.25. And keep in mind, because this is DOPs, MOPs transform is going to scale this thing by about 25% per time step. So this can get out of control pretty quickly, except that we have this noise field that's going to sort of scale everything back after the fact. I'll show you what I mean by that in a second, but without that, it would be very easy for these things, if our falloff values were much higher, for the entire simulation to scale out of control. So keep that in mind when you're determining these numbers. 25% per time step could end up being a lot if you don't have some counterbalancing force later to make sure that things normalize. And in fact, if I just play this as is for just a few frames, it goes out of control almost instantly. So we don't want to do that. So the next thing that I need to do is sort of come up with that counterbalancing force. What I want to do is have anything that's not being scaled up get pushed back towards the original goal scale and position and orientation. So what I'm going to do is basically just remap this fall off. I'm going to invert it. I'm going to do this with a pop wrangle. There's a few different ways you could go about it, but pop wrangles are easy enough to work with. And all I'm going to do with this wrangle is say that mops falloff 2, because I can have as many falloff attributes as I want, is equal to the inverse of the mops falloff from the noise field. So 1 minus mops falloff. The reason I'm not just overwriting the falloff value is because this is a simulation. I don't want to mess with mops falloff because it's not really running. DOPs, the way things are ordered is a little bit weird, and nothing really happens until the solver decides that it happens. So the safe way to go about this is to keep these variables separate so that I'm not overriding anything. I know it can get confusing, and it might not necessarily be an issue in this case, but this is my way of kind of playing it safe. The last thing that I'm going to do now is use apply attributes. And I'm going to use this apply attributes to basically match the original transforms of my goal object using this new falloff attribute that's the inverse of the original. So anything that's not being scaled up with this first noise falloff and transform is going to get pushed back to the original transform by the exact opposite of the noise field. So what I'm going to do to slow this thing down a bit, because I'm relying on the noise, the falloff, the inverse of that falloff field to be a certain value, is rather than tweak the falloff directly here, I'm just going to drop the force multipliers to be a bit lower, and that way these things don't snap too quickly back into position. So this is going to make it so that they kind of ease back into their original translation and rotation. The scale force I'm going to leave at 1 because I need these things to scale down quickly so that they don't completely blow up. I'm also going to turn off treat as wind. I don't really need this to be a wind force. I want these things to get back there pretty quickly. And then under falloff, I just want to make sure that I'm using mops falloff 2, the inverse, as my falloff value. Now let's take a look at this. So you can see that they scale up and then scale back down. And as they scale back down, they go back to their original position. Let's just set this to real time so we can actually see it happening. So you can see they scale up and they shove everything else out of their way because collisions are active here. But then once they start scaling back down as the noise field leaves, they sort of get dragged back into their original position and settle in. The last step then is to take this simulation and apply it back to the original packed primitives like we have before. So all I'm going to do is start with an extract attributes to make sure that I have all the template point attributes that I want saved to these things. And then I'm going to use an apply attributes to take these high-res pieces and match to the transforms of the low-res ones here. I'm just going to disable falloff because I don't care about that for this. And now here's all my pig heads moving along with that original simulation just as we wanted it to. Here's our next effect. We're going to build this rotating grid of cubes that is slowly spinning, so the goal is actually going to be animated in this case. We're going to blow it apart and then slowly reassemble it using falloffs. This is just using a single MOPs Apply Attributes DOP. It's got a little bit of setup going on, but you'll see how easy it is to do this once we get into it. So first I'm going to drop down a geometry container like always, and then a box stop. Let's add vertex normals so that they actually look correct when we instance them. Next up is the Mops Instancer. I'm going to set the uniform scale of these things to be about 0.15. And then for distribution, I'm going to leave it at grid, but I'm going to set this to be a 1 by 1 by 1 grid. And so now we have this 5 by 5 cube of cubes. Next up, I'm going to just transform these guys up a little bit so that they're not intersecting with the ground plane. So we'll just move this whole thing up by 1 unit so it has room to fall. Now I'm going to use a point wrangle to configure some initial velocity real quick here, because I want these things to have a little bit of push as they go out. There's a lot of different ways you can go about this, but the way that I've managed to make it work well for this is through a quick wrangle. So I'm going to create an initial velocity by normalizing P. And what this does is it means that everything is going to be basically pushing out radially. To visualize this, and also because we need to actually bind it to something, I'm just going to set v at v, so the velocity attribute is equal to this times, let's say, 5. So it's going to blow out pretty quickly. If I use an add stop to visualize these as points, and make sure I have point trails enabled, you can see that this is sort of the direction that they're all going to fly. So they're going to kind of blast outwards a bit. But I think these are probably going upwards a lot farther. I don't really want them to go up. I want them to kind of blast outwards a little bit. So what I'm going to do before I bind it here is just say that v.y, so the vertical component of velocity, is going to be equal to, we're going to fit v.y from -1 to 1 to 0 to 0.2. And so now you can see that everything kind of flattens out quite a bit. So they're still going to explode outwards, but not nearly as much as they were before. The next thing I'm going to do is add a little bit of randomness to this, because I think that this is maybe just slightly too uniform. So I can do this with a point velocity stop. And I'm going to initialize this with the incoming velocity, so that's my starting point, and then just add some curl noise to it. Turn off animated because I just want this to be a really quick explosion. And then I figured out some values earlier that look reasonably good for this. So this means that I've got like a good initial outward explosion, but enough variance happening in here so that it's not going to be totally artificial. Okay, I don't need this visualizer anymore, so I'm just going to delete it. And what I want to do now that I've got my velocity figured out is I want to configure the fall off. And because I know the order that I want these things to reassemble in, I want it to reassemble from top to bottom here. Rather than do the fall off in DOPs, which would take into account their new positions on the ground and make it a lot harder to determine the ordering, I'm going to do the fall off here and then import that into DOPs. So I'm going to just drop down a shape fall off here, and let's turn on preview. And I want to orient this so that it's going to hit the top first. So I'm going to rotate it back 90 degrees in X, and then scale it down maybe here. And then I want it to start up here somewhere, let's say about here at frame 1, and then keyframe this. I don't want this to start right away, so I'll move this keyframe over to about frame 24, so 1 second in is when the rebuild starts. And then at frame 120, I'll move this down to roughly, let's say like right here, and then key it here. So this is the time and the order in which these things are going to reassemble. So this fall-off value is going to affect the simulation once we bring it into DOPs. And that means that regardless of how these things explode and lay on the ground, the pieces that are on the top of this hierarchy here are going to get pulled back first. And that way we can avoid any sort of uncomfortable collisions from pieces underneath trying to push through to get to the top. Now, lastly, because I have p-scale, scale, and orient attributes here, as always, because this is CDD19, I'm going to use an attribute delete to get rid of those. So orient, p-scale, scale. Now, the next thing I'm going to do is configure my goal state. And if you remember, these things, I want them to be spinning over time, so these things are sort of rotating around slowly in their final goal state. So I want them to all be moving from a single central pivot, so I don't need mops for this. I'm just going to use a transform SOP. And I can go back up here to before I started doing all this velocity stuff, because I don't want that in here. And I'm just going to drop down a transform and have this thing rotating at 1 degree per frame. So I have this nice, slow, steady rotation. The visibility flag on there. There we go. So that's my animation. And finally,
because these things are animating and the orientation is changing, the intrinsics are updating, but the template point attributes are not. So I'm going to drop down and extract attributes. And this makes sure that I have the right goal attributes as template attributes for MOPs to recognize. And now we can wire these both into a DOP-net. So here's my geometry, my starting geometry, my initial conditions, and these are my goal conditions, and these will go into input too. So again, we'll start with the Rbd packed object and set the geometry source to be the first context geometry, and then put down a rigid body solver. And there's my initial conditions. The next thing I want to do is on the Rbd packed object, you have this option to decide what you want to overwrite. And normally this is things like active state, deforming state, things like that. But in this case, what I want to do is, because I'm animating Falloff in the SOPs timeline, DOPS isn't going to update that attribute unless I tell it to. So there's a couple of different ways that I could do this. I could use MOPs fetch attribute and actually pull this from the first or second, in this case, the first context geometry. I could wire this in and use it as solver. And this, with the default settings, would essentially do that. This would fetch MOPs Falloff from SOPs and just apply it directly to the DOPS geometry here. But the Rbd packed object has this built in, so I don't need to use this here. I'm just going to enable this, and then instead of active animated deforming, I'm going to use MOPs Falloff. And just so my visualizer also comes with this, because it just is going to make the Falloff easier to see, I'm also going to fetch CD. So now I got the color attribute as well. And now these are going to be automatically updated from the SOPs timeline on each time step. The other thing that I want to do is inherit velocity from point velocity. And this means that that velocity that I configured in SOPs is going to apply on the first time step here in DOPS. I'm also going to edit the bullet data here because this is a pretty small sim and the way these things are packed together has pretty tight tolerances. The default collision padding here is a little bit thick, so I'm just going to drop this to about half of where it starts at, so 0.01. And this should mean that these things can collide realistically and pack up nicely. Okay, before I get apply attributes involved in here, because I want these things to explode and then hit the ground, I need a ground plane. You can just leave that at default and then merge it in. Left affects right. And then wire that into the outputs, and now there's my ground plane. And then I need a gravity force, so I'll just wire that in at the end. And now if I play this, you can see that they kind of explode outwards a little bit and then do nothing. Although you can see that because I'm fetching Falloff and color, they change color over time. And so this is going to be the order in which these things start resettling back towards their original position. And this is where apply attributes comes in and play again. I'm going to wire this in here. As far as inputs go, I don't need to change anything because my goal is the default second context geometry, so nothing I need to do here. Everything that I'm going to be handling here is in force update. So all of these things are probably fine. I'm going to want more air and spin resistance because if I'm using this in wind mode and I want these to fight gravity, I need the force to be fairly strong. So I'm going to set these both to 10. And then the force and rotate multipliers, I might not want to be this high right away, but I'm going to leave them where they are for now, and let's just see what happens. So we play the sim and things explode, and then you can see that they do get back into position, but they're a little bit disorderly about getting there. Let's turn this to real time so we can see it happen. So they get there, but they get there very quick, and then they have these kind of fights where they're jittering around and trying to fight each other in order to settle into position. Let's just watch that one more time. You can see that they kind of struggle to get in there. So apply attributes has a few different ways for us to manage that sort of thing. And one of the nicer features that it has to address this is snap by attribute. So when we turn on snapping, there's a couple of different options that we have. We can snap by attribute or we can snap by distance. If you snap by distance, what it means is that if one of your points gets close enough to its goal, it's going to enter a snapping mode. And in snapping mode, they start ignoring collisions by default. You can see there's an option here, disable collisions while snapping. And they're going to switch from a force-based mode, whatever this force mode is that you picked here, to position rotation mode, which essentially means that they're going to ignore all physical forces and just try their best to get into that position without worrying about collisions in the default mode when you have this enabled. Snap by attribute means that you're going to look for, by default, the Falloff attribute, whatever you have set there. That's what this expression means. And if that attribute is above this or meets the snap threshold, that's how you determine whether something is snapping. So in the default settings here, if your fall off value reaches 1, then these things are all going to go into snap mode. The release threshold we'll go into later, but this basically means that if the fall off dips below this value later, they're going to exit snap mode and go back to using normal physical forces. So with everything here at default, just with our snapping mode enabled here, let's just rewind and see what it does now. So they explode and they go back in, but then they enter this snapping phase. So once they're, let's just watch it again really quickly here. Once these things have a fall off value of 1, so once they turn white, they basically go into snapping mode and they ignore collisions. They're just going to exactly try to match, and then eventually will exactly match their goal position and ignore everything else along the way, so you get a cleaner, more settled result. And the way that this works currently is once they enter that mode, there's this option called snap time, and this is the time in seconds in which they're going to blend from their current transform to the final transform once they enter snap mode. So everything is going to snap into place within a second of the fall off value reaching 1. Now we could turn that way down if we want them to snap faster. So maybe we want them to do that in like a quarter of a second. And so once these things reach white, you're going to see that they very quickly just pop right into place. You also have the option of using this easing curve in order to kind of finesse how they settle in. So if you want them to ease out towards the end of it, towards the end of that snap time, you can kind of build this acceleration curve into their movement once they've entered snap mode. You can also completely deactivate snapped objects if you want. So once these things reach their snap state, if you turn this on, this means that these objects are effectively static objects. They won't respond to any forces at all. So this won't really affect this simulation much. If you rewind and then go back here, they're going to settle into place and more or less do what they did before. But if we were to modify other forces later on or change other things about the simulation, if we were to take the ground plane and suddenly move it upwards, it wouldn't affect these things at all because they're completely deactivated. So if you really need these things to meet this final target and you don't want them to ever move again, this is a great way to do it. So in this example, we're going to be mixing together multiple goals with fall-offs. In this little destruction animation here, we're blowing up this little mirror-looking thing twice, and then reassembling it in 2 different ways to match 2 different goal patterns. Okay, so first things first, let's make the box. I'm going to set this thing's dimensions to be 0.5 by 0.8 by 0.01. So we've got this thin panel here. And then I'm going to use match size to first rest it on the ground plane here, and then I want to lift it up a little bit just so that we have a bit of room to fall. So 0.2 units seems fine. Next is to run Rbd Material Fracture. It's going to be a little bit slow, but this is what we're going to use to turn it into glass. Under the material type, I'm going to change this from concrete to glass. And then for impact points, I'm going to scatter 3 points so we get some more wild chipping here. Under cracks, I'm going to change the radial number to 34. And the seed to 4. These are just settings that I know are already going to work. The minimum width is going to be 0.084. Impact spread 0.835. And then a little bit of work on the discontinuity frequency. I'm going to set this to be 7.06. Move this to 41. And then a few other adjustments on the detail tab. This isn't entirely necessary to adjust now. We can do this sim with what we have. I'm just setting this to match the existing example file so that we get very similar results. 213, 46 for the noise amplitude, and then the noise frequency is going to be about 2.46. I'm going to enable convex decomposition because this means that my fragments are going to be broken apart into convex hulls, which is a good thing. Now the next thing to do is to pass these results into Rbd configure. So this is the main geometry, and then this is the proxy geometry, which goes into the third input. I'm going to set the physical attributes down here from concrete to glass. Okay, the next thing to do is to create my 2 animated goal states. And I'm going to do that kind of like I did with the last one, where I'm just going to use a transform SOP on the proxy geometry, because this is what we're going to run through the simulation. And I'm going to, let's say, rotate this around the y-axis, frame times 2. So this is going to spin around its center axis here vertically. And then I want to do something very similar with another one. I'm going to make another transform stop. And this one I'm going to spin around a different axis because I want this to be the one that rotates sideways. So I'm going to rotate 90 degrees along X and then rotate frames times 2 on the Z axis instead, so I get this spin. And then because this is on the ground here, I'm just going to do another match size to bring this up about 0.53. Okay, so now this is my secondary goal spinning around on this axis. They're both hovering in the air, but they're hovering in slightly different places and they're spinning on different axes. So in the simulation, we're going to blend between these two goals in between destructions. So the next thing I have to do before I go any further is I've got to extract attributes on both of these goals. This is to make sure that MOPS has template point attributes to work with when it's assigning these as goals. Now I'm going to drop down my DOP network, and let me just put down a null here so I have this laid out clearly. This here is a bunch of packed fragments, and I don't have template point attributes on here, so there's no worrying about deleting them. But this is my sort of default state here. So this is going to be wired into the first input. This is my first goal state. I'm going to wire this into the second input. And this is my third goal state. I'm going to wire this in here. Okay, let's dive inside. Now, as always, the first thing I need to do is set up an Rbd packed object. And I'm going to set the geometry source to be the first context geometry. Drop down a rigid body solver. And wire that in, and now I have my initial conditions. Also, just so I can see Falloff again, I'm going to enable solve on creation frame. You don't have to do this, but it does help if you're trying to line up Falloff in the simulation, which we're going to be doing. Before I go any further, the other thing I want to do here is create a ground plane because we're going to have gravity and collisions in here, so it makes sense to have one. I'll merge that in, left effects right, and then wire that to the output. Now I've got a ground plane. And then, of course, I need a gravity force. So if I just play this as is, it's going to fall and then shatter into a bazillion pieces. So the first thing I'm going to do is create a fall-off force that rebuilds it in order to meet the first goal. And I'm going to do that with a shape fall-off. So let's create a MOPs shape fall-off. And I'm going to set the shape in this case to be spherical. Now let's wire it in so we can see the gizmo here. That's a little bit big, so I'm going to set the outer radius to be a little bit lower than this. We're going to say about 0.8. And then I am going to start the scale of this thing pretty low. So let's drop it down to, let's say 0.2. So at the beginning of the simulation, it's not going to be affecting any of these points. And let's say around frame 13, I'm going to key that scale. And then at about frame 72, let's bring this up to 5 and then set another key. So now it's going to encompass pretty much the entire simulation. And then we'll let it sit here until frame 96, so give it another second to stay at that range. And then we're going to have it fall apart again by scaling it back down to nothing. So again, 0.2 I think is where we had it, scaled all the way back down. And now we have this fall off that's going to apply itself, which means that all of those pieces are going to get sucked in and then it's going to drop again. And if we want to see this, we can enable fall off preview. So you're going to see these things turn red and then turn purple again. Now, because these are packed fragments, that's why you're seeing them all change color at the same time. And that's a Houdini limitation. If you're trying to visualize color on packed fragments, they're all going to be one color. So unfortunately, unless you repacked these to be individual packed primitives, and that's going to be a lot less memory efficient, you're not going to be able to visualize fall off on these things very easily. It's just a Houdini limitation that I can't get past right now. Okay, so now let's create the force that's actually going to reassemble this thing. I'm going to create MOPs Apply Attributes and wire it in after this shape fall off. This is creating the default MOPs Falloff attribute, so that's what we're going to be using for this first apply attribute. So we'll leave that at the defaults. Under force update, I'm going to crank the air and spin resistance a little bit. We'll set them both to 5. And this is because, again, I have to fight gravity here, so I need a little bit more force than just 1. Otherwise, it's going to be too slow in meeting the target. But I am going to turn down the force multipliers a bit. So there's going to be a little bit less force applied, but it's going to resist falling a little bit more, and this is going to help once we have them close to being reassembled. The other thing I'm going to do is enable snap by attribute. I'm going to set the snap threshold to be, let's say, 0.9. This means that anything that has a falloff value of 0.9 or above is going to enter snap mode. And let's make the snap time a little bit slower on this one. So once they enter snapping mode, they're going to have about 2 seconds to get there. Let's rewind and see what this looks like. So they fall apart, and then as that sphere keyframes on, let's just slow it down here. As that shape fall off expands, you can see that the pieces in the middle start reassembling themselves from inside to out. And then they kind of just fall into place. This actually doesn't look too bad. Let's watch it again in real time. So the snap might be a little bit slow, and we could, tweak this by maybe we reduce the snap time to the default 1 second. See what that looks like. Let it fall again. Yeah, that's not bad either. And you can see that with the snap release threshold of 0.5, when the fall off goes back down again to, about halfway in the ramp is roughly green, you can see that that's when they start to shatter again. So they just immediately fall apart and act like regular rigid bodies all over again. And another thing we can do to maybe make this look a little bit nicer is you can see that these guys are kind of wildly rolling around all over the place, and that's just because with no other forces applied other than gravity, we don't have any air resistance to slow these things down. So we can probably just put in a pop drag and a pop drag spin in here. And we don't need the air resistance to be that high. I'm just going to set this to be 0.5 and this one to be 0.5. And now when they collapse, they settle in a little bit more. They don't wiggle around quite so much. There's still a little bit of wiggling that's going on, but we won't worry about that for this simulation. Okay, so now we've got to mix in that second fall off and meet that other goal. So I'm going to create another MOPs shape fall off. And like I did before, I'm going to make this a new fall off attribute because I don't want it to interfere with the first one. So I'm going to set this to MOPs Falloff 2. And this is going to be a linear fall off. So you can see it's already added this gizmo here. I'm going to go to the Shape tab, and when do I want this to show up? Let's just wait here. I want to give it a little bit of time, so maybe right around here is when it's going to start to wipe on at this point in the destruction animation. So I'm going to set this to be started at around 1.5 and 3. It's going to be roughly, I think I need to start them a little bit further out, maybe over here somewhere. Then I'm going to rotate this whole thing so that it's coming in from this side. So I can actually probably scoot that in a little bit farther. And now I'll keyframe the translate. And then 2 seconds later or so, I'm just going to slide the whole thing over, let's say maybe here, maybe a little further in. Yeah, right here should be enough coverage. And then keyframe that again. So this fall off is going to start sliding in around frame 120. And then all of these things are going to get pushed over to that second goal. That's the idea here. So the next thing I need to do to make that happen is I need to drop down another apply attributes. Now this one, again, I'm going to have to go to the Falloff tab and make sure that this is using the new Falloff 2 attribute. And also under inputs, my goal geometry isn't the second context geometry anymore. It's actually the third. I could also point directly to the SOP path if I wanted to, but because I've got it wired into the DOP net, I'm just going to go to third context geometry here. So now this thing is going to be pointing towards that other rotating glass piece. Everything else that we need to do is going to happen within force update. I'm going to make this guy assemble a little bit slower. So the air resistance I won't make quite as high so that it it'll try to settle in a little bit more slowly than the other one did. And then just like before, I'm going to enable snap by attribute, and then I think I'll just leave this stuff at default, so I don't really need to change this too much. So let's rewind and then see what this does. So it crashes, the spherical fall off, brings everything together, and then destroys it again, and now they all wind up and swirl into this second shape. This motion here looks pretty good. This is about what I'd want. This second one, the reassembly, you can see there's a little bit of a jolt there, and sometimes this is just a question of finessing a bunch of different settings, trying to adjust timing, figure out what's going on here. I think in this case what we can do is I'm going to decrease the air resistance and spin resistance a bit on the second apply attributes, so they're going to be a little bit slower to pick up and get started. And then maybe I'll half the snap time. So once we decide that they're snapped, they're going to reach that position pretty quickly. Let's try that and see what that looks like. So again, this first part I think looks good. It's the second one that's trickier. And so yeah, now that I've sort of tightened that up a bit, you still get that nice curling motion as they're picked up by this fall off to meet that rotating glass plane. But once they get curled up and they decide that it's time to snap, that happens pretty quickly. And so it has a little bit of a punchier movement that I like. Let's watch that one more time. There we go. So here we are. We've got all of this destruction happening and then rebuilding to match animation that's happening in SOPs. And this is a big part of sort of how the MOPs-DOPs workflow is intended. The idea here is that you should be able to set goals in SOPs where you can animate things really precisely and then use these different forces and snapping behaviors with falloffs to get your dynamics animations to roughly or exactly meet your SOPs animations, but still have physical responses and collisions and all that good stuff. And one more thing that I want to point out before we end this tutorial is that I've been doing all of these examples with RBDs, with packed primitives, right? With the bullet solver. But you could just as easily apply these concepts to vellum or to particles. Anything that uses forces, and most solvers that are not related to volumes in Houdini are using the same attributes to define forces, those will all work with MOPs. So all you have to do is just make sure that you're telling this thing to work with things that have an ID attribute, and you're matching by either name or ID. So if you were doing this with vellum or with particles, for example, by default, this thing thinks that you're going to be working with RBDs, and so it sticks to name. But you could just change this to ID, and now it'll work with particles or vellum. So keep that in mind. There's a lot of stuff that you can do here outside of just bullet dynamics, outside of packed RBDs.
Thanks for watching, and see you again soon.